Arantxa para traducir. So the thing I want to there are two things on this slide that are worth mentioning. Three things, perhaps. Two is a good number. Neptune is a blockchain that uses Starks all over the place. We don't even have a signature scheme. Instead, you just prove ownership of the funds that you are spending. And those proofs are being recursively proved away. And for that purpose, we use Triton VM, which is a Stark engine. And so that showcases that I'm coming to you with both research expertise as well as hands-on implementation expertise. And then the second thing I want to drive your attention to is that these slides are online. ASC.ink is my personal website, and I collected presentations, or some of the presentations I put around there. This presentation is already there, and so you might want to record that URL at the bottom of this slide, because there's a lot of information in here. Okay, let's get into it. I'll spend one slide motivating why you should be studying Starks, and then I'll run into a pipeline for producing Starks. I'm not sure I'll be able to reach the end of this presentation today, but that's okay because we still have tomorrow. And if I do, there's still plenty of material to cover tomorrow. So feel free to ask questions in the course of this presentation. I do like the feedback from the audience. Yes, please.
Could be a question.
No such thing.
Okay. What did the letters without your name in the previous slide mean?
That's my name.
Okay.
In Chinese.
Wait, tell me if it was.
Alan Sherpianians. It's a stretch to say that I can read this, because if you were to show me this in a different context, I wouldn't recognize it. And it's possible that there are even characters in here that are rare, and so maybe not everyone who studied Chinese can recognize all the characters in here. I actually don't know. But so Alan has a canonical translation into Chinese characters, but Sherpianians does not. And so you have to mix and match symbols to match the sound, and it's kind of difficult. And that's part of the reason why I always copy this, just in case there is a Chinese person in the audience, they'll be able to know how to pronounce my name, because apparently it's difficult. All right, let's get started with the motivation. Why do we want Starks? And I'd say the answer revolves around the distinction between virtual machines and fixed circuits. Basically, we have two ways of representing computations. One is through a automaton or a virtual machine, and the other one is through a direct circuit, a fixed circuit. So for virtual machines, these are versatile. You define the virtual machine once, and you write different programs for that virtual machine. And so since it's easy to write a new program, you have a low cost for each application. It does take a one-time startup cost to produce the virtual machine. But if you have a lot of different applications to cover, that's probably the way you want to go, because writing programs is easier than using the fixed circuit approach, where you have to design a new circuit for every application. And yeah, you can get faster circuits, faster proof systems, if you optimize for every individual application, but it takes a lot more effort. And this translates into proof systems as well. With a virtual machine-based proof system, you have one prover, one verifier, and many programs, however many programs you want. Whereas with a fixed circuit, your prover and your verifier are tied to the circuit. And so for every computation, you can decide whether you want to use a circuit representation or a virtual machine representation. But by and large, there are guidelines, and you might decide to deviate from these guidelines. But if you have, say, a blockchain application where you don't even have signatures, you have a Stark proof instead to demonstrate the owner's assent to the transactions, and you want to do transaction aggregation, and you want to prove the correctness of your blocks, and you have a whole bunch of different individual programs in the context of your blockchain, then you probably want a Stark engine. The condensed to a short phrase, if you have a whole bunch of different applications for your Stark engine, then you want a virtual machine. On the other hand, if you have one application or a small number of applications that you need to be very fast, then you want to hand optimize a circuit and hand optimize a prover for that circuit. And then maybe Starks are not the way to go. One important distinction between these two models of representing computations: in the virtual machine world, everything revolves around a state that evolves across time. You can think of the state as all the bits inside your processor as it updates its own state by fetching an instruction, reading memory, and performing some logical operations on its registers. Whereas in the fixed circuit model, there's no such thing as a state. You just have one very complicated relation between the inputs and the outputs directly. The reason why you might want to choose Starks, if you're looking for a proof system for one or family of computations, is because Starks are tailored towards proving the integral evolution of a state across time. Evolution of state across time. That's where Starks shine. And we see this reflected in the Ethereum Foundation's Drive project towards Starkifying or Snarkifying, rather, the Ethereum blockchain. This its proofs is right now it's a project that's just tracking the various zkVMs that might one day be capable or already are capable of proving Ethereum blocks. And the big takeaway is there are a whole bunch of zkVMs, and most of them are Stark based. And in fact, also most of them are hash based, and not all the ones that are hash based are necessarily Stark based. Okay, that was the motivation. Are there any questions so far? No, good. Let's dive into it then. Starting with the definition of Starks. A Stark is a scalable, transparent argument of knowledge. And this red definition is the one that you will find in the literature on the original paper that defined Starks. Transparent means there is no trusted setup. So there is a public parameter, yes. The public parameter is essentially which hash function are we using? And there's no secrets involved in producing that public parameter. Succinct means the verifier is efficient, but we don't just want the verifier to be efficient, we also want the prover to be efficient, so it can have at most a logarithmic overhead over just performing the computation. It's an argument because it's computationally sound, and it's an argument of knowledge because we can extract the witness. This is actually the only time in this presentation or the next presentation that I'm mentioning proof of knowledge. We can safely forget about it. It is a concern for theoreticians, but not for practitioners. According to this definition, Starks can be interactive or non-interactive. And there's a good reason why you might prefer interactive Starks, is because the communication complexity is a lot smaller. And also, according to this definition, it cannot have pre-processing, whereas according to the next definition, it can have pre-processing. Yay, there are multiple definitions. And so people often ask me, what is a Stark? And then I have to say, it depends on who you ask. Well, in another definition of Starks, we are looking specifically at a particular family of proof systems that uses an algebraic execution trace and an algebraic intermediate representation, AET and AIR, in combination with a deep Ali protocol or just an Ali protocol, which may or may not be randomized and may or may not have pre-processing, in which case it's a RAP. And it uses interactive oracle proof of proximity, which is a fancy word for saying low degree test, such as Freister or Word, and it uses Merkle trees. And this is actually the scope of this presentation, because if you say we throw out the hash function and we use lattices instead, well, you might still have a Stark according to the first definition, but you would not have a Stark according to the second definition, which is closer to the list of CKVMs that I showed previously. That's a question, yes.
What does ALI stand for?
Algebraic linking. It's a particular phase in the compilation diagram that's coming up very soon. All right, and then the third definition of Stark is the concrete string of data that represents the non-interactive proof in Stark 2. So if I send you a Stark, then it's saying I'm sending you a file. That file represents the proof. Okay, so let's get a conceptual overview first before I dive into the compilation pipeline. So we have a virtual machine, which is the diagram in the middle. We feed an input to the virtual machine, and the virtual machine produces an output. And that's how we decide to represent our computation. And we want to split this computation up into two parts, the prover and the verifier, such that the prover takes the input and the output, and produces a proof. The verifier takes this proof, as well as the original input and output, and decides if that original input and output is a correct pair, meaning that input is sent to that output. All right, and the central question in SNARK design, more general than Stark design, is how do we make this transformation possible? That's the big gray arrow. And here is the universal formula for making SNARKs. SNARKs are characterized by having a fast or efficient under some metric verifier. And so here's the formula. You give the verifier superpowers. The verifier becomes God. And then you start stripping away these superpowers one by emulating them using cryptography. And in the end, you end up with a concrete program that uses cryptography and does not have any superpowers anymore, but still inherits the asymptotical efficiencies that you designed using superpowers. Yes, questions. Hang on. Behind you, there was another question.
Sorry to narrow the question, but are these asymptotics well understood?
Are these asymptotics well understood? Yes, I think you need to make your question more specific if you want a more specific answer.
I mean, some sort of theory.
I'm not sure what a convergence theory would look like. Generally, we quantify the complexity of the prover in terms of the number of cycles of the virtual machine. And so the prover's complexity is allowed to be n times log n, where n is the number of cycles. And the verifier's complexity is allowed to be some polynomial of log n. And these are, big O notation complexities. So up to some constants. Other question?
Oh, yeah, so the virtual machine, if we can understand automata. This makes one of the same numbers.
Yeah, well, I'd say a virtual machine is more general than an automaton because a virtual machine also gets to read memory and write memory. And once you get to do that, you're basically a Turing machine. But how do you draw a Turing machine? I went for this diagram instead. But it's very close, and all the tools that I'm going to explain in the upcoming slides apply just as well, even if you restrict your family of computations to a simple automaton.
You understand that?
Yes. All right. So what kind of superpowers do we have? We're starting from this split where the prover takes the input and output and sends a proof to the verifier. The verifier takes that proof and the input and output. And we're going to design a verifier using superpowers that is efficient in some metric. Well, the first superpower is obviously interaction. You can ask the prover, can you please specify what you meant by this diagram about automatons? And then the prover has to provide a compelling answer. The next superpower is point queries. So the prover is allowed to send very large strings of data, and the verifier gets to ignore most of it and say, I want the value in that point and that point. And as long as it's a small number of points, you get to count only the complexity of the number of points that the verifier is reading this long string of data in. This is the IOP model, where IOP stands for interactive oracle proof. So this blue string that I drew here, that's the oracle, and the verifier is reading it in a select few points. And so it's easy to see why this is a superpower, because if the verifier were to read everything, it would take him very long. But we're designing the metric such that we only capture the number of elements from this vector that are being read. The next superpower is low-degree tests. So now this vector either belongs to a special family called a code, or it doesn't. And the verifier can test this membership. And in the specific case of Starks, we're going to look at Reed-Solomon codes. Specifically, that means that the verifier gets to see, does this vector correspond to the evaluations of some low-degree polynomial on a given domain? That domain is obviously going to be a lot larger than the degree bound. And so it has a unique answer. And in order to compute that unique answer, the verifier would have to read every element of this vector, but we're giving him a superpower so he can test it just like that. Right? Low-degree tests are pretty powerful because they synthesize information that's spread out across this entire vector into one bit. And then the next superpower is polynomial evaluation queries. So here, the idea is the prover is specifying some polynomial. You can think of it as saying, here are the coefficients of this polynomial, and the verifier gets to read the value that that polynomial takes in an arbitrary point, not limited to the evaluation domain for the code, as would previously be the case, but it can be an arbitrary point. So this is even stronger than the low degree test, because once again, it synthesizes information about the entire vector into one answer, but the answer lives in a finite field. It's not just a bit, it's a field element. Okay. And of course, depending on the superpower, your assumption is stronger or weaker. And so we're going to design a protocol that lives all the way at the bottom using polynomial evaluation queries, and then we're going to strip away superpowers until we get something almost boring, because in the end we want just a string of data. Yes.
So are you saying that in the end we will also remove interaction?
Absolutely. Yes, interaction is a superpower, and we are going to remove it. But like I said earlier, there are cases where you want to keep interaction, and so removing it is optional. And it comes at a cost, which I'll also cover. So the formalism, where you have a protocol between prover and verifier, and the prover gets to send long strings, long vectors of data, and the verifier gets to read only a few elements. That's an IOP, interactive oracle proof. Long vector is the oracle. And the formalism all the way at the end, where the verifier gets to read the value of a polynomial defined by the prover at an arbitrary point, that's a polynomial IOP. The notions in between don't really have terms, but it still helps to pause there for the purpose of education. So you can ignore the part on the left for a while. That's where the concrete constructions that make up Starks pop up. On the right is the compilation pipeline that's following the principle of giving the verifier superpowers and then stripping them away. So the strongest possible superpower is polynomial evaluation queries, and that's where we have the polynomial IOP. And so we're going to design one, a polynomial IOP that uses Stark principles, and two, a whole bunch of transformations. And in fact, the starting point for this, when it's specific for Starks, is the Deep Ali protocol. And then we're going to compile the Deep Ali protocol using these transformations on the right. And these transformations are generic, whereas Deep Ali is really the only specific thing. Now, this compilation pipeline doesn't quite link up to the computation that we were going to prove the correctness of. And so there's something missing. And what's missing is the transformation that sends the computation itself into something that can be proven. And this something that can be proven is not quite the same as the polynomial IOP. Polynomial IOP is a protocol for doing the proof and the verification. It's not the result of this transformation. So we start from the computation, and then we go through an arithmetization step, the result of which is a witness and constraints. And this witness and constraints, they live together with the polynomial IOP. Every stage in this diagram, in fact, has an associated witness and constraints. Well, maybe not every stage, but certainly the upper stages do. So unfortunately, the diagram has to be slightly sloppy at this point. But it still serves as a good roadmap for what we are going to cover in the next few minutes, or next hour, I'd say. It means that we get to start. More specifically, we are going to cover the Deep Ali protocol, of which the algebraic execution trace, AET, and AIR algebraic intermediate representation are integral components. And we're going to cover every individual compilation step. Starting with the arithmetization, all the way up here. The result of the arithmetization is the AET and AIR, algebraic execution trace and arithmetic intermediate representation. So, how do we arithmetize a virtual machine? To arithmetize means to represent in terms of field elements and polynomials. So we need to choose a field, and you might want to choose a small field if your computation is very large, because it means you'll have less data. But on the other hand, you also need a large field at some point if you want to use that field for soundness. And the polynomials that arise in your arithmetization should be of reasonably low degree. But obviously that degree has to be larger than 1 because you really cannot do much with linear polynomials. So here's one way to do it. This is what we're actually doing in Starks. The state space is just a vector of fixed length over the finite field. W many finite field elements, and W might correspond to the number of registers in your CPU, for instance. And this is a very simple example, but it's non-trivial enough to be meaningful, right? In this example, the state space is just 2 finite field elements. And that means that the initial state is x0 and y0. Yes, please.
But the 2 is for the sake of example.
Yes.
Okay.
Yes, so in this particular example, W equals 2. But in more general, more useful virtual machines and arithmetizations, W will be larger. So the next thing you need to define after state space is what does the transition function look like? The transition function sends the state at one point in time to the state at the next point in time. And it has to, well, I was going to say it has to consist of low-degree polynomials, and that's actually not quite true. You can find counterexamples because in the end, you're going to translate this transition function into a transition verification function, and that's the one where you want the low-degree requirement to apply to. But this is still correct in the big picture. All right, so the transition function, for instance, could be, it has to send, in this, continuing this particular example, it has to send 2 elements to 2 elements. So it is a vectorial function that operates on x and y and spits out 2 new values. For instance, 1 plus xy and x squared plus y squared.
Sorry.
Yes.
However, the x's with the indices are vectors.
The bold x's are vectors,
Yes.
and the not bold symbols are scalars. Yes. And when there is a subscript, it denotes a particular point in time. All right, and then the last thing that we need for the arithmetization to be complete is, well, actually, 2 more things remain. What does it mean? Both of which capture the question, what does it mean for this computation to be integral? Firstly, we need to say, what is the computation even, right? This, up until now, we've just described how it evolves across time, but how do we condense that into a claim? A claim relating input to output? Well, you look at the first state and the last state, for instance.
Right.
Yes.
And we are assuming, are we assuming that the output of the PM is a field element?
Yes. Well, actually, the output of the VM can be many field elements. And in the next presentation, I'll show how to make it such that it doesn't even have to be the very last subset of the very last state. But for the time being, let's pretend as though all the inputs live in the very first state and all the outputs live in the very last state. So that gives rise to a computational claim where you look at, where you fix particular values in the very first state and the very last state. And you don't have to fix the entire state. You can fix a subset. So for instance, that you could be fixing x0, first state x, first state y, and only x in the last state. That gives rise to a computational claim, which might be true or false. And this particular computational claim just so happens to be false. But it doesn't matter because the point of this example is to get across how you would go about defining claim in a way that's compatible with the mathematics that we need for sterics to work. Right, and then the last thing that we need is a definition of integrity. What does it mean for this claim to be true? Well, this claim is true if the boundary constraints are satisfied. The boundary constraints is literally the line above, the fixed values in the first state and the last state, and the transition constraints are satisfied, which means every consecutive pair of states satisfies the map given by the transition function. So this transition function sends the first state to the second state to the third, and so on, all the way down to the last. And if all of those transitions are true and the boundary constraints are satisfied, then the claim is true. That's how we define computational integrity. Are there any questions about this slide? Yes.
I'm just a bit curious regarding the last one, the Clayton polynomial. I know you're going to say what is it, but is it the one that checks that the first state, if you validate the first state in the verification polynomial, you get the last, or no?
No. So if you apply the transition function to state I, you get state I minus 1. You can rewrite this as f of state I minus state I plus 1 equals 0. And then you can split that single equation into more equations if you want. And then that's where the low degreeness applies. And there are a handful of examples, typically involving field inverses, where you cannot write it as low degree polynomials if you stay within a single equation, but if you spread it out across multiple equations, you can actually make it into a low degree equation. And by the way, what I just did by moving one term to the other side in order to get an equation to 0, that allows me to equate polynomials to equations. And since equations are constraints, polynomials are constraints. Implicitly, the polynomial represents a constraint that is satisfied if it evaluates to 0. There was a question here? Yes.
About that. So you can determine the constraint scenarios.
How do you determine the constraints in this scenario? Well, that depends on how you define the virtual machine. There has to be a rule book for deciding which arrow you take. And that rule book is a recipe for F, or rather, there is a bijection between F and the rule book for moving around in this finite state machine. Okay. So with that arithmetization in mind, we can finally define our very first Stark object, or very first object related to Starks, and that's the algebraic execution trace. So we have an execution trace if we collect the state of a computation at every point in time. And we have an algebraic execution trace if we do that using the arithmetization that we saw on the previous slide. So our state consists of W field elements, and we have an initial state, and we have a transition function. So we can start building a table, one row, that's our initial state. We apply the transition function, now we have another row. We keep applying this until our computation has terminated. And then we have a table. This table is the algebraic execution trace, AET. Question?
May I dare to ask if this can be seen as implicitly a proof of equivalence between the arithmetic circuit and virtual machine computation models?
I don't see that yet. I mean, there is an equivalence.
Or are we relying
Are we relying on the equivalence between the virtual machine and arithmetic circuit models? Yeah, well, I guess if you define your wires correctly and define your circuit as the k-fold or n-fold composition of F with itself, then you have a circuit. So that direction is obvious. The other direction is not obvious. So how do you go from a arithmetic circuit to a state machine? You would have to define an algorithm that actually walks down every wire individually. But that algorithm exists, and you can cast it into this arithmetization. So yeah, that isomorphism between circuit model and machine model does exist. It is very close, but it's not quite on topic here. Okay. So the AET is just a large table of all the values, all the state values across time. And then we need to define the constraints that capture in polynomial terms what it means for that trace to be integral. So the air, and going forward, I will not use the full term algebraic intermediate representation anymore because air is simpler. And because I wouldn't say it's a representation, I wouldn't say it's intermediate. It is very much algebraic. So air is better. It's a set of multivariate polynomials of low degree that capture the boundary constraints and integral evolution. In terms of polynomials, and so using the trick where we put all the terms on the right to the left, we get a polynomial equals 0. So the equation is the constraint, the polynomial represents the entire constraint because we can forget about the equals 0, or just remember to remember the equals 0 that's implicitly there. Okay, so we have the AET, and we have a bunch of different types of air constraints, starting with the initial constraint. This is part of the claim. Remember, we set x0 and y0 to something, and that would be an initial, that would be an air constraint, which we can capture in terms of a multivariate polynomial whose variables are identifiable with columns in the AET. So if we are looking at the first row in this trace, then our variables are x0. Likewise, if we are looking at the last row, then our variables are x and -1. We have n rows, and this x is bold, so it's a vector of variables. And in fact, it doesn't just have to be a set of equations, it can be some more general function of those variables. So now we have boundary constraints at the start and at the end, initial and terminal constraints. There are two more constraints, and in fact, you can add many more types of constraints, but there are two more constraints that are useful, or typically useful, or readily useful, I should say. The first one is transition constraints. These are the constraints that require for every consecutive pair of states that the second one results from applying the transition function to the first. And so here you see that trick in action. We have, you apply f to xi, you should be getting xi minus 1, and then you rephrase that equation by moving all the terms to the left. Okay, and then there's one more type of constraint, which is a consistency constraint, and this is typically useful if you want to decompose a particular register into its constituent bits, for instance. Then you want to say, if you sum all these bits in the right position, then you get that element. It's useful, but it's not strictly necessary, whereas transition constraints are strictly necessary. And without initial or terminal constraints, you cannot articulate meaningful claims. Okay, now the thing to remember, and the reason why I chose different colors to represent these constraints is because they aren't fixed. The red ones are not fixed to any particular column, whereas the green ones are. The green constraints, the boundary constraints, they are not quantified because they apply to fixed rows, which is the first row and the last row. In principle, you can extend this, but there's no reason to if your claim only pertains to the input and output of your computation. But the red constraints, the transition constraints and the consistency constraints, they are supposed to apply to every row or every consecutive pair of rows, and so they are quantified. And so we have a bit of a conundrum here, because if we are going to enumerate all of the constraints across the entire trace and let the verifier test every constraint, well, then the verifier's work is linear in the number of cycles. And we were hoping to produce a SNARK, a succinct proof. So we have to find a clever trick to get around this problem of quantification. How do we succinctly test quantified constraints? And the answer is we use a little bit of algebra and cast things in terms of polynomials that are or are not divisible by each other. So here's the bit of algebra. We take a polynomial which has known roots, and we take another polynomial that has exactly those roots and nothing else. So the blue polynomial is an arbitrary polynomial with the given roots, and the green polynomial is defined as the product of x minus root for every root. We call this the zerofier, and the rest of the world calls it the vanishing polynomial. The rest of the world is obviously wrong. It's obvious to see why it's called zerofier. It has zeros in the right position. So the theorem is a polynomial is always divisible by the zerofier for its root set. So if we have a zerofier that's defined in terms of the roots of that polynomial, then it's divisible. It's pretty straightforward. I see the mathematicians say, yeah, waving his hand, that's totally easy. It's actually not very difficult. So we define f, or we decompose f in terms of a product with some cofactor with the zerofier, and then We do not know a priori that there isn't a remainder, so we have to write that remainder, but we can know that the degree of this remainder is smaller than the degree of the zero fire. And then we start plugging in our roots, and we find that this remainder, when evaluated in every one of those roots, has to be 0. And the degree of this remainder is smaller than the number of roots of this remainder. And so the remainder has to be 0, and therefore we have divisibility. Okay, trivial bit of algebra, very powerful for producing stars. So we are going to use divisibility to get around the problem of quantified constraints. Yes?
But have you mentioned yet why we know the zero?
Why we know the zeros? I did mention this, but I don't mind mentioning again. These air constraints need to be satisfied, but simultaneously we are representing those air constraints as polynomials. And so by moving all the terms of the equation to one side, we have the polynomial, and implicitly it's an equation to 0. So the polynomial needs to evaluate to 0.
Yes. Because I'm not sure if it's more than one variable actually.
That's a great point. We will need to do interpolation. We're not going to do Lagrange interpolation, but a faster algorithm with the same effect. And then we are going to compose those polynomials with the air constraints. In the end, once again, getting a univariate polynomial where we can apply univariate divisibility.
But at this point, are they multivariate polynomials?
The air constraints are multivariate polynomials, but the divisibility will apply to univariate polynomials. And I have not yet explained how to obtain those univariate polynomials. That was the arithmetization. The deep Ali, which comes up next, explains where you get the univariate polynomials from. Because it is, after all, a univariate polynomial IOP, which means that the prover gets to send the polynomials to the verifier, and the verifier gets to read the values of those polynomials in arbitrary points in the finite field. Okay. And here's the intuition of the Deep Ali protocol. 1, interpolate the trace. Using Lagrange interpolation if you want, but there's actually a faster algorithm that you really should be using. Secondly, you compose these polynomials with the air constraints. This gives you univariate polynomials that should evaluate to 0 in all the locations where the constraints are supposed to hold. And you know those locations beforehand because you decide where you want to evaluate, where you want to interpolate those polynomials over. Now you have polynomials that should be divisible by known zero fires. And so you divide out those zero fires. Right? That gives rise to a very simple high-level protocol. And this is even more high-level than polynomial IOPs, because this verifier will be able to test divisibility directly. Prover interpolates the trace, sends over the trace polynomials. The verifier composes the trace polynomials with the air, and then tests divisibility by their zero fires. That's it. That's the protocol. Now I'm sweeping a whole bunch of things under the rug, and I'll visit them momentarily. First is soundness. You'll see that over the course of the rest of this lecture, whenever I present a protocol, I want your first reaction to be, what's the soundness of this protocol? And so let's try this. Here's a protocol. Yes, please. Where's the soundness? Exactly. And that's obviously missing from this slide. And you should not allow me to progress unless it's in a direction that's going to answer this question.
But also, how you progress if you have stated how is our soundness defined. Right?
The soundness is defined as the probability of a malicious prover convincing a gullible verifier. Well,
Yes.
this verifier isn't gullible, right? Because I'm presenting the verifier.
The one we have.
Yeah, the one we have. The probability of a malicious prover convincing the verifier of a falsehood.
It's an expression that Aranza had.
Exactly that expression. And falsehood is exactly an input-output pair that does not match. Yes, okay. The second thing is, I'm saying compose the trace polynomials with the air, and that makes sense because we have W trace polynomials, and some air polynomials take W variables, but the transition constraints take 2 W variables. And so there's no way to compose the transition polynomials of the air with the trace polynomials, or at least not yet. And then thirdly, this is not a polynomial ILP because the verifier has a superpower that is not captured by the polynomial ILP formalism. The verifier in the polynomial ILP only gets to make evaluation queries to the polynomial, whereas now he's testing a holistic property of polynomials. So this is too high level and sweeping too many things under the rug. Let's start with turning it into a proper polynomial ILP first. So we want to build the equivalent of a divisibility check using polynomial evaluation queries. So we're going to build a transformation that takes a protocol that assumes divisibility checks are available, but the protocol we're building doesn't have them available. It's going to emulate or simulate that protocol where they are available. So the protocol that we want to simulate is where the verifier directly checks divisibility. And the protocol that we want to build accomplishes this through polynomial evaluation checks. And it's actually not so complicated because what it boils down to is the prover performs the division, computes the quotient, sends over the quotient, and now the verifier has 2 polynomials, P, the original polynomial, and Q, the quotient. Moreover, the verifier knows the zerofier, and so he can evaluate all 3 polynomials in some random point Z. Question.
How does the verifier know Z? Like, doesn't
The verifier defines Z. It's part of his program code. F will correspond to the polynomials that correspond to the trace. So trace interpolants, that would be F. Yes. Later on, you will sum them. For now, we're not summing them, but at the same time, I'm zooming in on a single divisibility check between 2 polynomials. Implicitly, we're going to apply this trick many times to the deep Ali protocol that I showed earlier. Z comes from capital Z comes from the constraints. Small z is sampled at random. All right. Yeah, those of you who saw it knows what's coming next. Those of you who didn't can infer it by the fact that I just presented a protocol. So what should your first reaction be? Soundness, exactly. So soundness captures the probability that the prover is lying, but still convinces the verifier, which means that we're looking at the probability that as polynomials, this equation is false, but it happens to be true in the point z sampled at random by the verifier. Now this is captured exactly by the Schwartz-Zippel lemma. The number of zeros, if you move all the terms to the left-hand side, we have a polynomial of degree d, degree deg. It can have at most deg zeros. And so the probability that the verifier was unlucky enough to sample one of those is degree over size of the field. That's the Schwartz-Zippel lemma, and this is negligible. So we're good. Okay. There was a question here about how does the verifier know Z? And I realized I did not answer it in perfect detail. That's because there's some context to it. It's because in the context of the deep Ali protocol, Z corresponds to the domain where the trace is being interpolated. That's where we want the transition constraints, at least, to hold. So back to the deep Ali protocol. We can refine this. Previously, it used divisibility checks. Now it uses polynomial evaluation queries. And so the prover needs to compute the quotients, but that's allowed. The prover just sends the quotients over after computing them. Okay. I still haven't really answered soundness because there's still this lingering question, what's the degree of this polynomial? But the previous slide did go in that direction. So I should be allowed to deviate slightly before I get to answering this question properly. I haven't touched how we make transition constraints possible at all. But based on the previous slide, based on the question that was raised, how does the verifier know Z of X? Well, that's a new question. I didn't really capture that at all. And remember, Z of X corresponds to the points where we want the constraints to hold, which is all the points over which we interpolate the trace domain. And so the degree of Z of X corresponds to the number of points up to 1. And the number of points is the number of cycles in the computation that we ran. And so how can this verifier evaluate Z of X if its degree is linear in the computation length? Well, the answer is Z of X needs to be sparse. It's not an arbitrary polynomial because it's not an arbitrary domain. It's a structured domain such that evaluating Z of X is easy. Okay, so here's how to pick the right domain for your interpolation. We want to interpolate the algebraic execution trace, thereby getting trace polynomials. And the question is, over which domain do we do this interpolation? And the answer is a subgroup of the multiplicative group of order 2 to the k. And that's a mouthful. Just think of the complex unit circle. We want to interpolate this in evenly spaced points on the complex unit circle. If your first reaction is you cannot just associate the complex unit circle with the subgroup of a multiplicative, the multiplicative subgroup of a field, yeah, forget about that. It's okay. It really is okay. I'm quite sure there is a bijection here, and even if there isn't, it does capture the right intuition. So every one of these red circles on the complex unit circle will be associated with one row in the trace. And we can interpolate very fast, not using Lagrange interpolation, but using the NTT. This is essentially the same as the fast Fourier transform over finite fields. This gives us the n log n complexity of the prover. Interpolating, well, actually, another step that also involves the same algorithm, the same entity, is the bottleneck of the prover. Right, and this also gives rise to sparse zero fires, which is nice. Well, the zero fire for the first and last row, they're not very interesting because we're going to be low degree anyway. And so they will be low degree independent of your domain. But the zero fires for the transition constraints and for the consistency constraints, they are sparse now. Because using a fancy bit of algebra, the zero fire for all of these red points on the unit circle is exactly x to the n minus 1. And if you want to ignore the last row, as you want to do with transition constraints, well, then you just divide out the zero fire for the last row. And you don't actually compute the dense polynomial that you would get if you perform this division. You keep it like a numerator and a denominator so that you can evaluate it quickly. There was a question, yes?
Are you using interchangeably the words sparse states?
Nope, no. Sparse means the vector of coefficients of the polynomial consists overwhelmingly of zeros. And so if you start evaluating that polynomial, you only need to pay attention to a small number of terms.
Sorry, but
So concretely,
different round, but then the zero fire polynomial is literally x to the root the k minus 1 or something, or is
well, if n is the number of rows in the trace, then the zero fire polynomial will be x to the power n minus 1.
So, I mean, I guess one could, if one wanted more, say, theoretical details, one could ask for a proof of such sparseness, right? Or is it
Yes.
also?
The proof is not too difficult. Take any one of these red circles and raise it to the power n, see where you end up, and subtract 1. And that's your value. And that's 0.
Oh,
Exactly those points.
yeah.
There's your proof.
Oh, yes. Okay. But so, are you like forcing the zeros to be ones of that sort of root of unity?
Yes, that's the whole point. This sparse zero fire, x to the n minus 1,
Yes.
is the principal reason why we are choosing this domain.
I guess, yeah. So you just, if your n is not a power of 2, you just fit it as a sub-table of.
Yes, you add padding rows because the power of 2 is just too useful to not use.
Yes.
Okay. And then there's one other very useful thing that falls out of choosing this domain. Yes, go ahead.
Are you using Frobenius on the root?
Are we using Frobenius? No, we are not. All of this holds over a field, over a prime field. So no, we're not using Frobenius.
Okay. Yeah, normal. We'll just what you said, x to the yeah, normal.
Okay, so the last reason why this is absolutely the right domain to choose is because it gives us an arithmetic shift, which you can think of as rotating clockwise or counterclockwise by 1 point. And rotating what? Well, remember that we are interpolating the trace. So we get trace polynomials. And if we rotate the trace polynomials, then we get new polynomials that take the same values, except in the points after rotation by omega. That rotation is very simple to compute. And it gives us the polynomials that represent the next row in every x. So now we have two sets of polynomials, the current row, where if you evaluate that polynomial in omega to the power I, you get row I, and the next row, so that if you evaluate those polynomials in omega to the power I, you get row I plus 1. And so I'm going to define composition of transition constraints with air polynomials by taking into account this rotation trick. So the transition constraints, remember, take 2W variables, and now we're going to substitute those 2W variables with, firstly, the trace polynomials, and secondly, their rotation, which gives us every consecutive pair of rows if you evaluate it in omega to the power I. Okay, so that actually answers the problem of transition constraints. That's 2. And so the only thing that remains is soundness. Yes, the remaining question of soundness, which is what is the degree? And the degree follows from 2 things. We interpolate the trace, that gives us degree n polynomials, or n minus 1. And then we compose the trace with the air. That gives us polynomials of some degree that depends on the degree of the air. That's why the degree of the air has to be low degree. And then in some cases, we divide out zerofiers. So as long as the trace, well, in practice, the trace is always going to be small because we only care about computations that we can actually run to prove. So the trace is going to be limited, and the air is limited by design. That was the whole reason why I said up front that the air has to consist of low degree polynomials. And then indeed we do get a bounded degree. Yes.
So, yeah, the rotation, I guess, is just like silly, but so that it's evident. Well, sorry. So the continuous picture I have in mind is like you have your polynomial, of which you don't know the zeros, but then you bring it down so you can see the zeros. So I'm guessing that you do the rotation. If I may ask for the very last expression where you had this equal sign with the triangle above, what does that?
The equal with the triangle above is my way of saying I am defining the expression on the left to mean the expression on the right. And so what does it mean to compose transition constraints with a vector that only has dimension W, when the number of variables that the transition constraints take is 2W? Well, I'm defining that in terms of the shift. So in terms of the rotation. So you take the trace polynomials and their rotation, you concatenate them, and now you have a vector of 2W. That's the definition. Yes, I will get to you, but this person was first.
Yeah. This is not a tricky question, but why do we need to interpolate?
Because we want to use divisibility as a succinct way to quantify constraints.
Divisibility is on the evaluations or first in the polynomial, and then I apply simple lemma.
The divisibility applies to the polynomials, but the question is, how do you represent those polynomials? And in order to answer that, compellingly, we need to proceed further down the compilation pipeline.
Yeah. I can wait.
Okay. Your turn.
Interpolating the colors.
We're interpolating the columns, yes.
Just refer one T. So it's like there's one T for each color.
Yes, but this is a bold T.
Yeah.
So there is,
It's like a vector.
it's a vector of polynomials, yes.
Thank you.
Okay. So that was the Deep Ali protocol. Now it's time for the deep trick. Little note on this diagram. If we apply the deep trick to the Deep Ali protocol, we actually get something that's not Ali. Sorry, this is an error of history. The Ali protocol came first, and then they realized, hey, we can make this more efficient if we deepify it, and then if you do go in the reverse direction, you actually get a completely different protocol. And I wasn't sure what to call it, so I just left Ali in its place. You get something that resembles Ali in some respect, but it's actually concretely different. But still, this is a generic transformation, and the name of the resulting product shouldn't matter too much because it will be itself the input to the next transformation of this compilation pipeline. So, what is the deep trick? Well, the deep trick falls out of the principle whereby we strip away superpowers of the verifier. And so, we were operating in the polynomial IOP model, where the prover sends polynomials and the verifier gets to ask, what is the evaluation of this polynomial in this point, in that point, and so on. And we're going to move into what you might call a low degree IOP, where the prover sends vectors and the verifier gets to define new vectors in terms of old vectors using local maps. And the verifier also gets to perform low degree tests. So the entire vector goes into a low degree test, and then the verifier gets to know if it corresponds to a code word or not. And in this entire lecture, as well as the next, code word means set of evaluations of a low degree univariate polynomial on a given domain. And I've already covered which domain we're thinking about. Actually not, but it's close. If it's on the same picture, we'll get there soon. So we want to simulate polynomial evaluation queries using this more basic tool of pointwise maps and low degree tests. And the polynomial evaluation query is, well, the verifier selects a point and reads the value of the polynomial in that point. And the question is, what does this look like if we simulate it using more basic tools? And the answer is, we are going to represent polynomials. This is answering your question from earlier. We are going to represent polynomials by their evaluations on another domain, a larger domain, or a domain that is larger in terms of kind of cardinality than the polynomial's degree. Much larger by a significant factor. That's the read so on code. Yes.
Okay. Yeah. So sorry, but I got a bit confused. So you haven't yet been 100% explicit of what the code word looks like if you know the polynomial.
Correct. That's what the next section is about.
Okay.
So we are identifying polynomials with their code words. And once we have a code word, it is in fact a vector. And this is where we are taking the domain from. We're looking at the same unit circle. We're looking once again at evenly spaced points, but their number is a small multiple of the number of trace points. And we're also going to shift them by a small degree alpha. Now this shift is not strictly speaking necessary, but it's convenient and it doesn't hurt. And I think it also gives nicer pictures. So we're going to first interpolate the polynomials, and then we're going to evaluate them on the same unit circle, but a different set of points. Which means that we can reuse the NTT. The NTT does both interpolation and evaluation. And so this step where we use the NTT to do evaluation, that's typically the bottleneck in the Stark prover. Now is a good time to introduce the concept of the code rate. That's the rho Greek symbol. It is just the number of trace points to evaluation points, which corresponds to, what is it, the ratio of information to redundancy in your code.
Picture that would be smaller than 1, right?
Yes, the rate is smaller than 1. 1 over the rate is the multiple that gets you from the number of red circles to green crosses.
Okay, so okay, so the trace valuation domain has size 1 over rho times n.
The other way around. The evaluation domain has size n over rho.
All right, and then you add trace, then it's some cosine.
Yes, well, we typically choose the subgroup for interpolating the trace and the coset for evaluating the resulting polynomials.
Could you one last time what the object of size 1 over rho times n is?
1 over rho times n, that's, I don't think that corresponds to anything. So the trace has n rows, and so there are n points in the trace interpolation domain, and n over rho, since rho is smaller than 1, this gets you a bigger number,
Yes.
that many points on the evaluation domain.
So it's the number of points on the.
N over rho is the number of points on the evaluation domain. Yes.
Okay.
Yes. Okay. So we are interpolating the trace, then composing with the air, and then dividing out the zerofiers. And then we continue by evaluating the trace polynomials as well as the quotient polynomials. And now we have a commutative diagram. We can either go right first, then down, or down first, then right, and we get the same result. Conceptually, it's easier to think of if you go right first, because then you have polynomial divisibility that you're using. But in practice, it's more efficient to go down first and then right. But it doesn't matter. Yes, he was first.
So are we going to then, in what follows, use some sort of inherited algebraic structure on the code space?
Are we using inherited algebraic structure? Yes, we are. Because in order to compose the code words with the air, you need to select from well-spaced points. You need to select pairs of rows with the right number of rows apart. So that's where the structure pops up. Yes. You cannot do this if the structure is not present.
Is this, if I may call it algebraic structure, and we have it on the whole code space, or just for the, is this one-to-one, or?
I'm not sure I understand this question.
Yeah, it's just like if we can afterwards, let's say, forget about polynomials if we wanted to, and you just treat, codes as an algebraic object.
Yes, we can. That's what we do in practice. And the only reason why it pays to write polynomials on this slide is because they are more intuitive. You have a question?
Just a comment. I think this slide is commodity diagram is the answer to my question. My service but now it's the at the very end, you're gonna evaluate on some random.
Yes.
That it's supposed to be on the whole. Yeah.
We're going to evaluate in a random point that doesn't even live on the unit circle. Somewhere in the field.
Not even
Not even on the coset. That's if you're talking about the deep trick, right? What is it in the low degree IOP and in the IOP models down below, the prover sends code words, and every code word there represents the evaluation of some polynomial on the evaluation domain, which would be on the unit circle. Exactly. The out of domain sampling is for boosting samples. Yes. What was D?
Yes, like you have the code word, to evaluate this on
Yeah, capital D.
Oh, that's the domain. Capital D is the domain. And that's the, in this case, that's the set of green crosses. Yes, every code word is a vector, but not every vector is a code word. That's where we use the low degree test to distinguish. Yes.
Sorry, but maybe my guess would be that my friend here and I also could complain about some abuse of notation with regards to the boldface P.
Boldface P.
Because in principle, polynomial is a point in ring of polynomials. So
Oh yeah, so D is a set of points. And so if you evaluate a polynomial in a set of points, then you get a vector. So this, it's so common that it doesn't qualify as abuse of notation anymore. But yeah, the way you were taught about polynomials in high school is you only get to put in a scalar. Yes. Okay. So we covered this commutative diagram. And since we're moving down first and then right, and we don't really stop in the polynomial phase anymore, we just merge those two steps. Interpolation followed by evaluation on a larger domain becomes one step called low degree extension. And by the way, since this diagram commutes, doing the low degree extension does not stop us from composing with the air. It just means that now we are evaluating the air on well-spaced rows instead. Okay. So let's have another try to compile polynomial IOPs into low-degree IOPs. Here's what we can do. The verifier sends, after picking the out-of-domain point Z, the verifier sends Z to the prover, and the prover responds with the value of the polynomial in that point. And then the verifier defines a new code word using a pointwise map. So the verifier doesn't actually compute this map because that would take too much time, but he can define it without having to compute it in every point of the code word. And so this map is exactly, we subtract the value at Z and we divide by the zerofier at Z. Note that DI is the ith domain point, which you can think of as the evaluation of x minus z in the ith domain point. And so this really is the value of the zero fire for z in the ith domain point. And so we use that to update the ith point of the code word by first subtracting the evaluation at z. This is just another application of the divisibility theorem. So if P was a valid code word, and if P of Z really is the correct evaluation at Z, then Q must be another valid code word. What's coming next? Soundness, yes, I just showed you a protocol. Your first reaction should be soundness. Well, okay, I guess I mixed the order of my animations. The verifier still needs to verify the low degreeness of both P and Q. But how sound is this? Well, there is an easy answer and there is a difficult answer. So we're interested in the probability that this vector Q is a code word, even though the value with which it was computed, the supposed evaluation y with which it was computed, does not correspond to the polynomial p for which the vector bold P was the code word. I feel that there's a slide missing, but I know that we will get there later. For now, let's look at realizing this test. Low degree test, we are verifying, or trying to verify that what the prover presents to us, which is a bunch of vectors, are in fact Reed-Solomon code words. And unfortunately, this thing doesn't exist. So we want to have a black box that we can put vectors into, and it will tell us yes or no, depending on whether it is a code word. And it just doesn't exist. So ideally, if we put in a code word, the probability that this black box rejects is 0, because it should only reject non-code words. And if we put in anything that's not a code word, ideally, the black box should say, that's not a code word, and reject it. So ideally, we have this sharp Heaviside function going up to 1 immediately and then staying at 1. I'll get to your question later. But in practice, we cannot really achieve this ideal behavior. Instead, we can only approximate the ideal endpoint, which is having a high likelihood of rejecting falsehoods, if we restrict attention to vectors and to vectors that are either, if we restrict attention to vectors that are either in the code or far from it, then we can approximate this ideal decision power. So the difference between the red line and the ideal blue line, that's the epsilon, and we know that this is negligible. The problem from this graph is we can only get to this negligible point if we ignore all the vectors that are somewhat close to the code but not quite in it. So either vectors are in the code or they are far from the code, because in the middle we can't really decide much. If they're far from the code, then we have this close to optimal, close to ideal behavior. But until we get to that distance, there isn't much, so we have to guarantee that we're always working with codes, we're always working with vectors that are either code words or far from code words. Far from is defined in terms of relative Hamming distance. So you take the Hamming distance to the nearest code word, and you divide that Hamming distance by the length of the code word. You had a question.
So please correct me if I use vocabulary wrong. So as you say, we are mentioning Hamming distance. So our codes are a very specific subset of strings over an alphabet, let's say.
Yes.
So now are these? So I'm gonna call this Reed-Solomon code space or something, which has our algebraic operation given by our mapping. So is this Reed-Solomon code space exactly the image of our interpolation map or evaluation map?
Yes.
Okay.
Oh, no problem. Time is over. All right, do I have time to finish this section and then we postpone the rest of this compilation pipeline to the next session? All right, so that gives rise to a rather nasty soundness analysis because we have to restrict attention to vectors that are far from the code. The computation becomes dirty. So we are interested in the probability that a working vector that we update using this deep trick or using the single point evaluation, that this vector becomes close to the code, even though we started from something. But we don't care whether the vector that we started with was close to the code or not. We do care about that no code word close to that vector corresponds to a polynomial that evaluates to y in the out of domain point z. So that is a mouthful, and if that's challenging, stay away from the paper. I will just summarize the result. It is a probability that's negligible if the list size is not too big. This list size, of course, this is the list of code words that are close to the original vector P. This list size grows with the radius delta that we are considering. And so this puts us into the realm of conjectures. If we select an arbitrary point corresponding to our vector and consider the code, and then consider expanding radii delta, what is the size of the list of close points? And it turns out that there's a gap in our knowledge here. In the unique decoding radius, we know for sure that, so if the radius is smaller than 1 minus rate over 2, then we know for sure that the size of this list is at most 1. And so in that unique decoding radius, all the analysis is easy. The list size is provably polynomial up to distance 1 minus square root of rho. But between 1 minus square root of rho and 1 minus rho, we don't know. And after 1 minus rho, the list size is provably exponential. And so the conjecture relating to list decodability of Reed-Solomon codes states that this entire region where we don't know about the size of the list is actually still polynomial. Right up until the covering radius, the size of the list is polynomial. This is one of two conjectures that features in Stark. And so that allows us to determine whether this soundness probability is negligible or not, because whether the size of this list is polynomial or not depends on the radius. And if it is polynomial, well, then it's dwarfed by this 1 over field size for a sufficiently large field size. And so for every point, for every region in the picture earlier, we either know or we don't know, or we conjecture that the list size is polynomial and thereby get a negligible soundness error. So going forward, I'm not going to copy this expression on the right. I'll just denote this by epsilon 0. So this allows us to finally answer the question about soundness of the deep trick. We don't have exact low degree tests, but approximate low degree tests that force us to consider vectors that are either in the code or far from it. And based on that forcing, we can use the expression on the previous slide to capture the soundness. So in summary, deep Ali plus deep is you low degree extended trace, evaluate the error, divide out the zero fires, apply deep in a random out of domain points, and the soundness is all the terms we accumulated previously plus the soundness error that we accumulate from deep. Well, previously, we accumulated only one term, but you can imagine that going forward in tomorrow's lecture, this expression will become a little more complicated. The point is that complicated expression related to the decoding of list decoding of Reed-Solomon codes, that expression is now part of the soundness error. All right, that was Deep Ali and the deep trick. I think the remaining stages of the compilation pipeline have to wait until tomorrow.